That's interesting. I guess, yeah. It made something like that before my last class, and I was like, I don't know what that is. All right, today we're going to get into electric potential. And I'm actually going to start with the clarification right now, just in terminology. I saw questions about this on Perusal. Electric potential is okay, change color. Electric potential is the same thing as voltage. And oftentimes we'll drop the word electric and just talk about the potential. And just like if we measure potential energy is always measured against a specified reference point. Electric potential is always measured against a specified reference point. So I saw people questioning if potential difference was the same as any electric potential is always a potential difference between point A and point B. So don't let the words hang you up. Electric potential voltage is the same thing, and I'll talk about it later. I just wanted to make sure I got that off my chest now, since there seemed to be a lot of consternation about that. These pictures are useful, but we'll get into it because first we need to talk a little more about electric fields. So electric fields, what you have learned, a little frustration there apparently. What you've learned about electric fields so far is that an electric field is equal to the electric force divided by charge, which for a point charge, so this equal sign is only if you have a point charge, is equal to KQ over R squared. And since I have a vector equation, I need to put the R hat. That's what you have learned up to this point. And you learned about directionality, specifically that electric field lines, I can't eat lunch at the same time when I take one. Electric field lines point into negative charges and out of positive. Why? Because they point the direction that the force would be if I were to put some random positive charge nearby. And since opposites attract, a positive charge would be attracted to a negative charge. Hence, electric field lines point in. So when we talk about test charge, we're saying if I were to bring some random positive charge, that's what test charge means. So we have a new construct that we call electric field lines that simply are lines that show the directions of the electric field. And so if I have a single point charge, let's say I have a positive charge right here. If that's positive, what direction should electric field lines point? Out. And so they're going to point like this, out. And since force is equal to charge multiplied by electric field, if I were to bring a positive charge to any location, the direction of the force would be in the direction of the electric field line, and the magnitude of the force would be the electric field strength multiplied by whatever that charge is. And of course, if I brought in a negative, using those same rules, it would be an outward force with a negative magnitude, but a negative magnitude means opposite direction, so it turned into an inward force. No, okay. If I have minus 1 microcoulomb times 10 newtons per coulomb east, my answer would be, if I have remember those numbers in my head, minus 50 micronewtons east. But minus 50 micronewtons east translates into plus 50 micronewtons west. Andy.
Something that I think you've answered, but I still feel fuzzy on. If the charge of a point isn't mentioned, do we assume it's positive?
Yeah, for calculational purposes, assume it's positive, because if it's negative, you do all your calculations in it, with your equations. And if you put a negative number, it's just going to reverse the direction.
Okay.
So yes.
Awesome. Thank you.
So we have these things that are electric field lines to help us understand how we're going to calculate the charge in any random place. I'm sorry I used this last class, but I forgot.
Wait, I'm confused. So.
I thought she's like, wait, give that back. Go ahead.
No. So it's saying that like we're not supposed to use vectors to show electric fields. Then
Actually, we do use vectors to show electric fields. In our calculation, I have you use magnitudes separate from the direction, but they're still vectors. We just do magnitudes separate from direction. That is, like in the homework problem. Let me actually raise the board here just to point out something with the homework problem, because I think this is what you're asking about, Anna. And let me mute this, because yes, it has an AV mute. So we had a problem in homework that was asking us about the electric field at point P due to 2-point charges.
This is problem 2.
Yes. Problem 2, yeah. And the problem asks you first to find the x component of the electric field due to charge Q1. So following what I was just saying to Anna, thinking if I'm not understanding your question, you're going to have to just, when I'm done, say, no, that wasn't it.
Okay, that's fine.
Okay, so if we have this charge here, if this is a positive charge, what direction should the electric field point at any location? Out. And so at this location, the out direction is that way. So we have the electric field due to charge 1 is pointing that direction. And then we find its magnitude, K times charge 1 divided by the separation between charge 1 and this location squared. And so this is the magnitude of that electric field. And now we have to wind all the way back to early in first semester. We have a vector and it has components in the x and y direction. So we need to break that vector into its components. So if this angle is theta, this is the adjacent side. Cosine theta is going to be the adjacent side divided by the hypotenuse. So that means if you solve for E1x, you get E1x is equal to E1 cosine theta. And so there we've broken it up into, now we have the x component, that was answer A. And then for the y component, opposite side, remember, sine theta is opposite over hypotenuse. And so if you solve that for the opposite side, you get E1 sine theta. And that was answer B. So we broke the vector into its components. So going with what Anna, I think, was trying to say, remember I said at the end, you just have to tell me if that's not what you're saying. We did the magnitude, and then separately we did the direction, breaking it into components.
I just, from that like slide that you were on before you raised it or whatever, it was saying that like vectors didn't work, and that's why I'm confused, because then it went on to like electric lines or something.
I'll have to look back at that then. And
Maybe I read it wrong. I don't know.
Well,
I just, it seemed to be saying that like vectors weren't. I don't know.
Okay, so when I bring it back, we'll get back to it. So something we've all done before, but we need to get back to the practice of breaking forces into vectors. In this case, it's not a force though, is it? It's an electric field, but we still use the same process, breaking it into components. I said breaking into vectors because my brain skipped a beat. Then for part C, you find the electric field due to Q2. Q2 is negative, so what direction do electric field lines point with respect to a negative charge? They point in. And so that means the electric field due to Q2 is going to be pointing straight down. So the homework doesn't ask you about the x component because it's all in the minus y. And so your magnitude for E2 is KQ2 over y squared, y being the separation between these two. One more thing, just to make sure that we all are talking the same language. When I have sine and cosine here, you can physically find theta, right? They gave you x, they gave you y, so you could say, tangent theta is equal to y over x. Theta is equal to arctangent of y over x. But it's really much easier to simply say r is, using the Pythagorean theorem, square root of x squared plus y squared, because you have to use that right here. And then cosine theta is equal to the adjacent side, x, divided by the hypotenuse, r. And so instead of actually calculating cosine theta, I just replace cosine theta here with x over r. And likewise, sine theta, opposite side over hypotenuse. So I do this problem without ever actually calculating what the angle theta is. Sarah, you had a question.
Yeah, wouldn't that one be negative k q2 over y2?
Well, Q2 is a negative value, so if I leave it like this, it's going to be pointing down. And so what I would traditionally do is actually put absolute value, find the magnitude of E2, and then my E2 in the y direction is negative because my arrow was pointing down. So you have to, at the end, when you get to the components, have it's negative in the y direction because it's pointing down. How you get there, I always say you use your reasoning in your brain to put that sign on it. Because you know what the direction is, you know that means it's in the minus y direction. So I find the magnitude and then I bring in the components.
So how are the vectors not being used for magnitude then?
Well, vectors have magnitude. And so I found the magnitude, E1 and E2 were the magnitudes. And then I broke them into components because they are vectors. And so you have the direction with the magnitude for the vector. And so when I broke them into the x and y components, right, part A was find the x component, part B was find the y component, then I have my full vector because I have the two components for each direction. So I started working with just the magnitude, and then when I applied the directions, I got to the full vector. Now, to look for the words that she actually was asking about, I wanted to make sure I went over that. Where is it that you were having a problem with this slide? Besides the fact that I should have had this word up there.
It just says it's often difficult to make one, and then because it becomes impossible to distinguish. So I thought it was getting at we don't really do so.
Okay, it's often difficult to make a visual representation of the electric field using vector arrows. So what that's saying actually is moving forward to another couple slides. If you have more than one charge, you have lines from this one go this way, lines from this one go this way, and you have to figure out what happens. And so we're going to look into that as we go through. So electric fields are vectors, and so they add together as vectors. So in the situation like I just explained, if I have a positive charge here and a positive charge here, the electric fields are going like this from each. Well, we just take the two vectors and add them together to get the resultant direction. And so electric fields can then have funny shapes if you have more than one charge instead of just being radial. Radial meaning going in or out from a point. And at any point on an electric field line, the electric field is tangent to the line. Tangent means in the direction of the line. So at this point right here, okay, I got to change colors because I'm in green, it turns out. At this point right here, a tangent line is like this. And so the electric field at that point is going that direction. So if you have electric field lines, the direction of the electric field line can be read by just looking at the direction of the line at any point. That's the direction of the electric field at that point. A second thing is, if lines are closer together, the electric field is stronger. We can actually see that looking at my little picture. The electric field for a point charge is kq over r squared. It's strongest closest to the charge. And if you look at the spacing between my electric field lines, they're closest together right next to the charge. And they space out as you go out farther, indicating the electric field is getting weaker as you go farther away from the charge. So spacing tells you about the relative strength of the electric field line, or the electric field. So here's a picture like I drew for a positive charged electric field. For a negative charged electric field, what if I have both of these in the same area? Then I have to add them as vectors. So if you look at this, well, in this region, the vectors are pointing the same direction, so it's just going to be a strong electric field in that direction, right? But here, I have one going up and one going down. If I add those together, I get a horizontal. And so what we're going to have is something that starts out radial, but then is going to deviate to look something like this. I already did that one. Notice there are directions to these electric field lines still, because it's a vector, it has direction. I couldn't make out the question.
I like drawing it, and then I looked up, and there were new things.
Oh,
So-
okay.
Sorry.
Now, here's another important thing about electric field lines. Electric field lines always start or end at electric charges or infinitely far away. You can't have an electric field start or end at some random point. So in this preceding picture, if you look at R, you can't have a new electric field line start there. Right? It has to start out at charge or end at a charge. And so that R is showing, okay, this is what the electric field magnitude would be at this point, but it's not part of the electric field lines, which is why it ends as well. So this is a rendition of what I tried to do on the previous page. You can determine the relative sizes of the charge. I know somebody asked, can we use, electric fields then to find the charge? If we count up how many lines come out of this or go into this, it will tell us about how big the charge is. In fact, that's what Gauss's law is. Gauss's law says if you measure how much electric field comes out of a region, you know how much charge is enclosed. And so in this case, I have 1, 2, 3, 4, 5, 6, 7, 8 lines going in. Going in means it has to be a negative charge. 8 lines gives me a relative strength. Over here, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 lines going out. What does it mean that the lines are going out? It's positive. And because this has 12 and this has 8, that means the ratio of these charges must be 12 to 8. Of course, 12 to 8, that's, you divide both numbers by 4, that's 3 to 2. And so these have to be a ratio of 3 to 2. Now, that didn't tell me this was 3 and this was 2 necessarily. There is a mathematical relationship, Gauss's law, that does give you exactly that. But for the Physics 152 class, we're not going to go over Gauss's law. So this is a practical application of Gauss's law, but we're not doing the calculations of it. It's not so bad. Let's say that you had a hypothetical test question. And the test question said, I have okay, if I have a picture like this, and this one says it's 2 microcoulombs, how much is the strength of the second charge? It's what? You have proportionality, but I told you what this one is. So with the proportionality, knowing what is, you can determine the other. So start with the easy. Is it a positive or negative charge? Positive. How do you know it's positive? Because they're pointing out. So you know it's positive. And then how big is its magnitude? It has 6 lines going out. 4 lines going out was 2. So how many does that make it? 3. Because for this one here, every 2 lines going out was 1 microcoulomb. So if it has 6, for every 2, it's 1 microcoulomb. So you can determine the charge, and that is the practical application of Gauss's law.
How does that apply with like the connecting ones?
I would just still count the lines around a specific charge.
Okay.
It doesn't matter where you choose as long as if you cover everything, it's going to come to giving you the total charge that you enclose. So just make sure you enclose 1 charge, and it doesn't matter where you cut it. Right, if I cut it right here, I'd have the same result as if I cut it like that.
Right.
So why are they giving us different charges than?
Well, in this case,
Why?
like I said, this one here has 8 lines. This one here has 12 lines. And so that tells us that the ratio between the two, right, if I didn't have the numbers there, I know the ratio between the two is 12 to 8, which is 3 to 2.
Okay.
And then since one is conveniently 2, the other one's 3 for the ratio of 3 to 2. Okay, something that cannot happen. Electric field lines cannot cross. Why can electric field lines not cross? How do you find electric field based on what we just did? Okay, we start with straight lines going out, and then when we have electric field from this charge and this charge, how do we find the resulting electric field? What made it curve?
You try to between the charges.
We were adding the two vectors. And adding two vectors to the tail. Yeah. When you add the two vectors, you only get one answer, right? You can only have one direction at any location. And so if they cross, that would indicate two directions. You clearly didn't add them right. So, right, you can't have two vectors cross because you're adding them together. If you add these together, you're going to get, something different. Or to put another logical way, since the force is in the direction of the electric field, at that point, if you had the electric field lines crossing, what direction would the force be?
0, right?
It would have to be the vector sum of those two, which is what the electric field lines should be. So electric field lines can never cross, but they can start or end at a charge or going out to infinity. We don't worry about the going out to infinity because you know where we never are? Out at infinity. So it's impossible for electric field lines to cross because they're the vector sum of your fields. This is actually leading us into some cool territory. Talking about conductors. What do you know about a conductor?
It's easy for electricity to pass through it.
Okay, it's easy for electricity to pass through it. You're thinking about charging through conduction. So conductors, it's easy for electricity to pass through. That is, electrons can move virtually with no energy loss. I say virtually with no energy loss, so that means for our general physics calculations here, we say no energy loss. So in a conductor, electrons can move freely. Now, let's take this picture at the left. Let's suppose that at this location, we have the electric field is pointing straight down. Then this says force, but let's say the electric field is pointing straight down. If the electric field is pointing straight down, what direction would the force be on a mythical positive charge because it has a little plus there? Force is equal to electric field times the charge. So if I had a positive charge and the electric field is down, what direction is the force?
It would also be down, right?
It'd also be down. Now, the charges are stuck here. They can't leave. But if I have a downward force, I can break it into components. One component that's parallel to the surface and one component that's perpendicular. That parallel component is going to make the charge move along the surface. Question, Krista. Claudia.
Just to clarify what you just said, if the positive charge is pointing down, then it's the same direction as the force?
If it's a positive charge and the electric field is pointing down,
Okay.
since the force is electric field multiplied by charge, if it's a positive charge, then the force is the same direction as the electric field.
Thank you.
So that charge would move along the surface. Because it's a conductor, the charge is free to move, so it's going to move. So that electric field would not be something that it could have in equilibrium. You could have in a transient case. We're doing what we call electrostatics, so everything's going to be in equilibrium. And so in equilibrium, it turns out you can't have an electric field in any direction other than straight out or straight into a surface, i.e. normal to the surface. So the reason you have to have electric field lines normal to the surface is because if they weren't normal to the surface, it would create a force in the charges to make the charges move until you reach equilibrium, in which case the charges wouldn't have that force making them move, and the electric fields would have to be normal. So electric fields always point directly out of the surface. So every part of the surface, they're pointing directly out. But that brings up a very interesting outcome. Excess charge will cluster at sharper points. The sharper the point, the more charge you're going to have there to keep that electric field always normal to the surface. So if I have something with a sharp point like a needle, and I have something with a dull point like my fist, I'm going to have more charge concentrated at the tip of the needle, and I'm going to have a stronger electric field there. Now, one group had to measure how much voltage, which is a word that, if time shall last, we'll get to today, how much voltage there was on the Van de Graaff generator. And how did they measure that? They measured the maximum distance they could draw an arc.
Yes.
But you might remember that little thing, okay, it was periodically making arcs just within itself. Let's ignore those. But you also had kind of a background sizzle sound. And that was electricity going into the air because there's a certain voltage per centimeter that the air can withstand. If the electric field is too strong, it will cause charge to pass through the air, even if I'm not out here with the ground. And so what's happening, the charge is passing through the air, it's leaving, or entering, depending if it's positive or negative, the source. So this brings us to lightning rods. A lightning rod is a sharp, pointy object. Why is it sharp and pointy? Well, just look at the electric field lines here. They're much closer at the tip, right? What does it mean if the electric field lines are closer? It's a stronger electric field, which means up here you're going to have a strong enough electric field that you are going, now since this is positive, you're going to have electrons coming in. It's going to pull in electrons from the air because of that very strong electric field. And if you pull in electrons, what's that doing to the charge on the needle tip? It's bringing it closer to zero. If you had excess electrons, you'd have electrons leaving, bringing it closer to zero. If you have missing electrons, it's pulling in electrons, bringing it closer to zero. So it's draining off the excess charge no matter which way it is. Why would that be useful if we're having an electrical storm?
Because it keeps like the whole structure from getting charged.
Yeah, it drains off excess charge in the structure. Lightning, as we saw from the group that talked about lightning, I have some slides coming up about lightning as well. Lightning is going from the negative bottom of the cloud to the positive surface of the earth. And if you drain off the positive of the earth, the lightning is going to go somewhere else where it's more positive. And so the lightning rods are draining off charge so you don't have lightning strikes. So you're not trying to draw lightning to that lightning rod. You're trying to dissipate charge so you don't have lightning. So if you look at the church over here, okay, used to be different orientation when I taught in Jordan's and Hall. If you look at the church over there, if you look, you will see that there's these little rods about this tall all along the eaves. And those rods are, of course, not there to poke birds or anything like that. They're there so in the event of an electrical storm, it drains off charge so the church doesn't get hit. What does get hit almost every time we have lightning? The clock tower.
Is it really?
Yeah.
There's like something running a little bit though, right?
I don't know anything about the clock tower. I've never gone inside it or outside it either. But it's a big metal object that's got some reasonably pointy surfaces that sticks way up there. It's got all the things that make lightning say, there's a good place to hit. Okay, I didn't even load up the woo clap. I'm just worried about time.
It's fine.
What's the point of lightning rods?
You can direct the-
It's like a pellet.
No,
That's
not
what
switch
trans
lightning. I can explain this with more words, but I don't understand how it relates to these answers.
But there's
Oh, it's A.
Oh, it's B.
Okay, we have something like this
they're used to prevent
so that we can drain off the charge. And if you drain off the charge, what's that doing? Decreasing the electric field.
That's cool.
But isn't that
But it's not at the point.
like, just doesn't like propelling lightning correlate with B? Or just like
That's why I said the primary goal, not the secondary effect. The primary goal is to drain off the charge, which then has the secondary effect of it doesn't repel lightning, it doesn't push it away, but it makes you less likely to have a lightning strike. Yes?
if you're touching the clock tower when the clock tower got hit by lightning, would you then therefore get hit by lightning by proxy?
Okay. This is a good question. Lightning safety is always important. Some of you know Aaron Kent on one of the IRR trips. He got struck by lightning. Who?
Yeah, okay. He's Aaron Kent. Let me tell you. Like, it's gonna happen.
It's gonna happen
It's
there.
gonna happen to him.
Okay, so safety is an important thing. One of the funniest things that I can remember is when I was in college, we're in the car with my mom, and there's lightning around. She's like, "Quick, kids, get out of the car! Lightning!"
What?
Yeah, no, stay in the car, stay in the car. And well, same idea. See, earthquake, get out of the car. No, it's really much safer in the car. Anyway, lightning safety. First things first. If you're out in the middle of the field and there's lightning, like if your hair stands on end, you should be worried, right? I remember changing sprinkler pipes. The hair on my arm starts to stand up, and I'm carrying this big metal pipe. That wasn't very smart, right? So I at least put the pipe down. Don't want to be really crazy. What should you do?
We should do this.
Okay? Works for me. The fetal position. Not because you're scared and crying,
Yep.
but because you're reaching in a combination of minimal surface area exposed and not being very sharp and pointy. So fetal position is what you do if you're stuck out in the open. Hey, there's a tree. Should I run to it?
Yeah.
No, because theoretically they say if you're like within 20 feet of an object that lightning strikes, you got struck. Yeah.
Yeah.
So the trees tend to get struck a lot more, and if you're next to it, yeah.
But it's like a way less, like if you get directly struck by lightning, like you're probably gonna die. But if you get struck by lightning having struck something else, that's the people that get struck and have like the cool scar thing. Like that's a survival, not guaranteed survival, but that's a more survivable strike.
A more survivable strike. But I would
Yes.
prefer not to get struck at all. And then the fetal position is going to make you more likely to get struck at all. But if you get struck, yeah, you can die. But hey, okay, moving on. What about the car? Because you asked me a specific question, I'll get to the car and then I'll ask you because I don't remember your case. In the car, if your car is a traditional car, it's made out of metal. What electrical properties does metal have? It's a conductor. That conductor is going to let charge move freely around it. As a result of that, you know what you always have inside of a conductor? Zero electric field. Zero electric field because the charge moved around and made it so there's nothing on the inside. And so if you're inside a fairly closed, right, I mean, of course, if it's convertible, the top's down, then all bets are off here. But if you've got a metal cover over you, and except for the windows, it's all metal, you're reasonably safe from a lightning strike. Lightning can hit that car and you're okay. And furthermore, somebody pointed out, you have rubber tires. Well, lightning strikes your tire, you know what's going to happen? It's going to arc from your car to the ground, and it's probably going to go through the tires because that's the closest point between metal and the ground, and it's going to probably melt your tires or make them fail. But you're inside and you're pretty safe. So being inside a car during an electro storm, good place to be. Okay, so your question was if you're touching like the clock tower and the clock tower gets struck. Your resistance, something we haven't learned about, is going to be about 1,000 times bigger than the resistance of the clock tower, which means the amount of electricity that would go through your body compared to the amount that goes through the clock tower is fairly minimal as long as the clock tower is grounded at least as well as you are. So it should be relatively safe. But it'd be even safer if you were far away.
Did you go to school the other day, or were you here when he?
He was one of my students in physics.
Yeah, what was he like before
The same.
He took the principles of physics class. Okay, so I have a question here that relates to things that I've just said. Now we're going to work this through. This is not a calculational problem. This is a theoretical or conceptual problem only. So a thin metallic spherical shell of radius r carries a total charge of q, which is positive. The charge is spread out evenly over the shell's outside surface. Why is it even? Why would the charge be evenly spread out on the outside surface of the shell instead of unevenly?
Because that's how
Isn't it symmetrical?
Because it's symmetrical, it's got to be spread out evenly. If it was asymmetric, it would be more in the parts that are sharper and less in the parts that are flatter. Okay? Sketch the electric field lines if the shell is tiny and you're viewing it from far away. What does the sphere look like if you're far away? It looks like a point. So for that one, we're just going to have a positive charge. What direction do electric fields go from positive? So it's just going to go like, right? If you understood the things I've been saying this morning, that was pretty easy. Part B, you're looking at the field inside the shell's cavity. So you're inside the shell. What does it look like for the electric fields inside? Charge is all along the outside. What did you say, sir? She said, never mind. All the excess charge is on the outside. What's the charge on the inside? 0. What's the electric field then? Also 0. So my inside picture, I just leave blank because there's nothing in there. So here's the picture from the outside. Here's the picture showing the whole thing. This here, wrong. We could go back to what I told you about Gauss's law. Gauss's law, I said, the charge enclosed is proportional to the number of electric field lines going in or coming out. And so if I made a sphere inside of that sphere, how much charge would be enclosed by that sphere? By all the charge is on the sphere, there's nothing inside. And if there's no charge, that means I must have the total number of electric field lines going in and out being 0. And since it's symmetrical, the only way to attain that with the symmetry is to have no electric field. So Gauss's law is actually usually how we get to that. Okay, we are so ready to get to voltage. Thank goodness. This here is actually exactly what you're doing in one of your homework problems. Now, the first line is if I have 2 parallel plates and one plate has a charge of plus Q and one plate has a charge of minus Q, then the electric field between them is uniform. That means it's all the same direction, all the same strength, with the strength of Q divided by epsilon 0, that's the permittivity free space constant, times the surface area of the plate. That's something that one student in here will prove mathematically, and the rest of you will work with.
Good luck.
So what's the A stand for?
A is the surface area. So A is this area right here. And M is the mass of an object you put in between the 2 plates. And so if we have these 2 plates, it creates an electric field. And then if I introduce a charge of mass M and charge Q, for instance, an electron, that's what you have in your homework problem, then the net force divided by the mass is equal to the area. But the net force is QE. And so I take this electric field, which has this magnitude, and multiply it by charge Q, divide by the mass, and that gives me the acceleration. That's exactly what one of your homework problems is. Just going from, we have an electric field, we put a charge in there. Because I have a charge in the electric field, there's a force, and because there's a net force, there's an acceleration. Taking you through the steps, bringing you back to chapter 4. Was it 4, 4 and 5? Newton's second law?
Yeah. I think I remember this.
So, a point here, the reason you can't take physics 152 before 151 is because we rely on the knowledge you learned. Last homework, well, actually, it's this homework assignment still. We had vectors and resolving things into components. We have applying Newton's second law. These are things that we have, at this point, they're taken for granted that you learned them first semester. And since you all did reasonably well first semester, yeah. I mean, you know the majority of students get A's in this class, right? Yeah. Carrie Wolf says, you got to tell the students because they all think people get low grades in physics. Anyway, so I assume you can do that. If you can't, come and we will brush up. Okay. Electric potential energy. That's the topic of the day. Chapter 19. So, electric potential energy. We learned that the electric force is just like the gravitational force. That is, force gravitational was capital G M1 M2 over R squared. The electric force was K Q1 Q2 over R squared. And so if we calculate potential energy, the potential energy calculation is going to be pretty similar. And so just like a rock falls to the earth, and you can talk about in terms of converting potential energy into kinetic energy, a charge, a positive charge will fall into a negative charge, and you can talk about the positive charge converting potential energy into kinetic energy. So, again, I'm just blurting. What direction does a charge accelerate? It always does one of these things. So whether it's an electron or a proton that's free in space, which thing does it always do? Does it always go toward, and I said charge, but we could talk about a mass charge as well. What direction does a mass charge go? Does it go to higher energy, lower energy, or higher voltage or lower voltage? It goes to lowest energy. It tries to go to lowest potential energy, being specific. So an electric charge will be accelerated toward lower potential energy as well. That's the way physics works. So why? This is not working. I tried it on this computer. It's not working either. So I got to figure out these plugins again. Update the Office and something breaks. We can calculate potential energy. One student, we'll call her Isabel, asked if everything was calculus. And the answer is yes. This is not a calculus-based class, so we don't use calculus in this class. But pretty much everything that we've been talking about since the first day of class is based on calculus. Newton invented calculus because he figured out there's no math existing to work on the problems with Newton's second law. And then once he invented it, then it's applied everywhere. And all of the stuff that we're doing here is calculus-based. And right about now, there's a lot of problems that you really have to solve with calculus. So David's class is now diverging a bit from yours, as he would definitely tell you, because he can actually do these calculations. So change in potential energy. We learned first semester, change in potential energy is minus, we define it as minus the work from a conservative force. An electric force is a conservative force. And work, in the non-calculus class, we said force times distance, right? Force times distance parallel, or force dot distance to be more specific. And if we were working with constant forces, that works. But this electric force is definitely not going to be constant in most cases. Oddly enough, in my scenario here, it is. But in most cases, like if you have a point charge, the force changes as you move. And so you really have to use the calculus form, the integral form, which is why I show the integral form here. I don't expect non-calculus students to understand the integral form, but that's really the only way to do it. And if you have a uniform electric field, such as this very special case, then it turns out that the change of potential energy is minus the charge times the electric field parallel to the change in position. So, and of course, you can all point to the student who's going to be doing more things than you in this regard. Yeah. So potential energy is something we can calculate based on the motion of a charge in the electric field. If the charge moves parallel or anti-parallel to the electric field, then work will be done. What happens if the charge moves perpendicular to the electric field? No work done. So there was again discussion about equipotential surfaces. Equipotential equal potential energy. So equipotential surfaces are surfaces where if you move along that surface, there's no work done, which means it has to be perpendicular to the electric field lines. So for a point charge, what direction do the electric field lines point? Either blank or blank. Either in or out. They're radial. And so the equipotential surfaces have to be perpendicular to the radial, so they're forming spherical surfaces. Now, in the textbook, you saw circles because it's showing a two-dimensional layer, which is circular for a sphere. Yes?
Okay, you just said if it's perpendicular, there is work. If it's parallel, there's no.
Other way around.
If it's perpendicular, there's no work. If it's
Right. If the motion is perpendicular to the electric field, then there's no work. Because the force is parallel to the electric field, and if your motion is perpendicular to the force, there's no work done. I'm sure I said work one too many times in that sentence. Okay, so let's look at this picture just to get some ideas about energy and work. So if I have a positive charge here, and the positive charge moves parallel to the electric field, the force on a positive charge is the same direction as the electric field. So if it moves parallel to the electric field, it moved the same direction as the force. Is that positive work done or negative work done? If I push you this direction and you move this direction, did I do work on you adding energy, or did I do negative work and take away energy? Added energy. So that's going to add energy. The charge is going to speed up, so its kinetic energy is going to go up. And its potential energy is going to drop because it converted potential energy into kinetic energy. So if a positive charge goes with the electric field, it's going to accelerate, go faster. Its kinetic energy increases, its potential energy drops. This picture here is just the opposite. It's now going against the force. So it's going to lose kinetic energy and gain potential energy by doing that. So just so we can see the visualization. You can't see a lot in electrostatics. So we show you pictures and hopefully you can build mind images of what's going on because you don't see electrons moving. Something that is important to keep note of. When I talked about what happens to a charge, I said we could talk about a gravitational charge. A gravitational charge mass falls toward the Earth, which gives it a lower potential energy, right? But there's only one type of charge for gravity. Mass is always positive. For electric force, there's two types of charge, positive and negative. And so if I have a positive object here and if I have a negative charge, what direction is it going to, quote, fall, end quote? Toward it or away? Positive fist, negative point. Toward it. But if I have a positive point up here and a positive fist, then what direction is it going to, quote, fall?
Away.
Away. In both cases, what did it go toward? Lower potential energy. Because a positive negative potential energy is smallest when they're touching. A positive potential energy is smallest when they're infinitely far away. So different behaviors, but always going toward the lowest potential energy. Once again, a bunch of calculus. How do we get the potential energy between 2 point charges? There is no way to do it without calculus. So I don't expect you guys to sit down and write calculus equations here, except for David. So basically, you have to kind of glaze your eyes and say, there's something occurring here, but the end result is when you do calculus, you end up with the potential energy equation is K Q1 Q2 over R. Now, the naive person says, I see what you did there. You just took the force equation, multiplied it by R. What's so special about calculus? But that's not what happened. Even though that's what looked like what happened. So, because the dr in that was not the same. But the potential energy is K, that constant, times charge 1 times charge 2 over the separation. And man, am I out of time. Here's a graph showing gravitational potential energy as you get far away from a massive object. It's very negative if you're close, and it goes up towards 0 if you get far away. If you have a positive charge here and a a positive charge out here, then that's what your electric potential energy looks like as a function of distance. It looks exactly the same. But if I have, actually, excuse me, a positive and negative. If I have a positive and a positive, then it looks different because you have two types of charge. So we will have to end there. I will give you some kind of watered down homework because we don't really have too much we got into voltage yet. But you will be able to calculate potential energy between charges, and so I'll go up that far. Have a great day, and I'll see y'all Friday.